previous video, we introduced machine learning in public health and built predictive models using logistic regression, decision trees, and random forests. Today, we're taking the next step into modern machine learning by focusing on two of the most powerful predictive algorithms used in healthcare and public health research: random forests and gradient boosting, specifically XGBoost. These methods belong to a class of techniques known as ensemble learning. Rather than relying on a single model, ensemble methods combine information from many models to generate more accurate and reliable predictions. In public health, these approaches are increasingly used for disease risk prediction, hospital readmission forecasting, outbreak surveillance, mortality prediction, and precision medicine. By the end of this video, you'll not only know how to fit these models in R, but also how to understand what they are learning and how to compare their performance in a scientifically meaningful way. So let's get started. In this analysis, we're going to build and compare two powerful machine learning algorithms, random forests and XGBoost, to predict whether a patient has heart disease. Our goal is not only to build accurate predictive models, but also to understand why the models make their predictions. That's where techniques like feature importance, partial dependence plots, and SHAP values become especially valuable. The first thing we do is load all the packages needed for the analysis. The Tidyverse package helps us manipulate and visualize data. TidyModels provides a unified framework for machine learning in R. Ranger is a fast implementation of random forests. XGBoost provides gradient boosting algorithms that often perform exceptionally well in predictive tasks. VIP allows us to examine feature importance. PDP helps us create partial dependence plots so we can understand how predictors influence outcomes. ShapViz calculates SHAP values, which provide local explanations for machine learning predictions. Finally, DoParallel enables parallel computing, allowing us to use multiple CPU cores and significantly reduce training time. Next, we load our heart disease dataset. Before building any models, we need to understand the data. So using the structure function, we get a snapshot of how many observations we have, the variables available, and the data type of each variable. We can see that our dataset is a data frame containing 1,888 observations and 14 variables. Each row represents a patient record, and each column corresponds to a clinical or demographic feature. The variables include age, sex, chest pain type, resting blood pressure, cholesterol level, fasting blood sugar status, resting ECG results, maximum heart rate achieved, exercise-induced angina, ST depression during exercise, ST segment slope, number of major vessels observed, thalassemia status, and the target outcome. Most variables are stored as integers, indicating either numerical measurements or encoded categorical values. The variable old peak is stored as a numeric variable with decimal values reflecting a continuous measurement. The target variable is binary, coded as 0 or 1, representing the absence or presence of heart disease. Overall, the structure confirms that the dataset contains a mix of demographic, physiological, and diagnostic predictors suitable for cardiovascular risk analysis. The summary statistics provide a clearer picture of the distribution of each variable in the dataset. Age ranges from 29 to 77 years, with a median age of 55 and a mean of approximately 54.4 years, indicating that most patients are middle-aged or older adults. The sex variable has a mean of 0.69, suggesting that around 69% of the sample is male. Chest pain type, coded from 0 to 3, has a median value of 1 and a mean of 1.14, indicating variation in symptom presentation across patients. Resting blood pressure ranges from 94 to 200 millimeters of mercury, with a median of 130 and a mean of about 131.5. Cholesterol levels range from 126 to 564 milligrams per deciliter, with an average close to 247 milligrams per deciliter, showing substantial variability and the presence of some very high values. For fasting blood sugar, the median is 0 and the mean is about 0.15, meaning that only a minority of patients exceed the clinical threshold represented by a value of 1. Resting ECG results are centered around category 1, with a mean of approximately 0.60. Maximum heart rate achieved ranges from 71 to 202 beats per minute, with a median of 152 and a mean of roughly 149. Exercise-induced angina has a mean of 0.33, indicating that about 1/3 of patients experienced angina during exercise testing. The old peak variable, which measures ST depression induced by exercise, ranges from 0 to 6.2. Its median is 0.8 and mean is about 1.05, suggesting that most patients show relatively low levels of ST depression, although some cases are considerably higher. The slope variable has a median of 1 and a mean of 1.42, while the number of major vessels observed, represented by CA, is typically low, with a median of 0 and a mean of 0.73. Thalassemia status is concentrated around category 2, with a mean of 2.66. Finally, the target variable has a mean of approximately 0.52 and a median of 1. This indicates that about 52% of the observations correspond to patients with heart disease, producing a relatively balanced outcome distribution for predictive modeling. Having reviewed the structure and summary of the data, we can now move on to data preparation and pre-processing. First, we check for missing data, as it is a major concern in public health research. If important information is missing, our model can become biased or fail entirely. The results show that every variable contains 0 missing values. This means we do not need to perform any imputation and can proceed directly to pre-processing. Next, we convert several variables from numeric codes into factors, allowing R to treat them as categorical rather than continuous variables. Variables such as sex, fasting blood sugar, exercise-induced angina, and the target outcome are also given descriptive labels like male, female, disease, and no disease to improve interpretability. This is an important data preparation step because many of these variables represent categories rather than numerical quantities. Converting them to factors helps ensure that statistical analyses and machine learning models handle them correctly while also making tables, plots, and model outputs easier to understand. After conversion, we use the glimpse function to verify that the transformations were successful, confirming that categorical variables are stored as factors and continuous measurements remain numeric before proceeding with further analysis. We can see that all the variables are now in the right format. We will now begin exploratory data analysis. Our first visualization examines the distribution of heart disease outcomes. This allows us to determine whether the dataset is balanced or imbalanced. Class imbalance is important because it can strongly influence model performance. And on the bar chart, we can see that the number of patients diagnosed with heart disease is slightly higher than the number without heart disease. However, the difference between the two groups is relatively small, indicating that the dataset is fairly balanced overall. This finding aligns with the summary statistics, where approximately 52% of observations were classified as having heart disease and 48% as not having heart disease. And from an analytical perspective, this is a positive characteristic because class imbalance is minimal. Machine learning models trained on this dataset are less likely to become biased toward one outcome category, allowing them to learn patterns associated with both disease and non-disease cases more effectively. Next, we compare the age distributions of patients with and without heart disease. Looking at the histogram, we can observe several interesting patterns. First, both groups are concentrated within the middle age to older adult population, with the majority of observations occurring between approximately 40 and 70 years of age. This is consistent with what we know from epidemiological research as cardiovascular disease risk generally increases with age. Patients without heart disease show a particularly strong concentration around the late 50s and early 60s, with a noticeable peak near age 60. In contrast, patients with heart disease appear to be distributed more broadly across the age range and show a greater concentration in the early to mid 50s. Another important observation is the substantial overlap between the two distributions. Many patients in their 50s and 60s are represented in both groups, indicating that age alone does not perfectly separate individuals with heart disease from those without it. This overlap highlights an important principle in public health and clinical prediction. While age is a well-established risk factor for cardiovascular disease, it is only one piece of the puzzle. Other factors such as cholesterol levels, blood pressure, exercise-induced angina, chest pain type, and indicators from cardiac testing also contribute to disease risk. The fact that we observe patients with and without heart disease across nearly the entire age range suggests that a multivariable machine learning approach may be more effective than relying on age alone. Algorithms such as Random Forest and XGBoost can combine information from many risk factors simultaneously, allowing them to detect complex patterns that may not be apparent from a single variable. In the next step, we prepare the dataset for predictive modeling by splitting it into separate training and testing sets. We first set a random seed of 123 to ensure that our results can be reproduced. We then divide the data using an 80 to 20 split, allocating 80% of the observations to the training set and 20% to the testing set. By using stratified sampling based on the target variable, we maintain a similar proportion of heart disease and non-heart disease cases in both datasets. Next, we apply five-fold cross-validation to the training data. We divide the training set into 5 equal folds and repeatedly train the model on 4 folds while validating it on the remaining fold. This process continues until each fold has been used as the validation set once. Again, stratification ensures that each fold preserves the original distribution of heart disease outcomes. These steps help us build more reliable models, reduce the risk of overfitting, and provide a more accurate estimate of how well the model is likely to perform on unseen patient data. Next, we prepare a modeling recipe that defines how the data should be pre-processed before fitting any predictive model. We specify that target is the outcome variable, and all other variables in the training set are used as predictors. We then apply dummy encoding to all nominal predictor variables. This step converts categorical variables into a numerical format by creating binary indicator variables, which allows most machine learning algorithms to process them correctly. Next, we remove zero variance predictors using the step_zv function. This step eliminates any variables that have only a single unique value in the training set, since they do not contribute any meaningful information to the model and can potentially introduce noise or inefficiency. Together, these pre-processing steps ensure that the dataset is properly formatted, clean, and ready for use in downstream modeling pipelines. Now we define our first model, the random forest model. We specify that we want to tune 3 key hyperparameters: the number of trees in the forest, the number of predictors randomly sampled at each split, and the minimum number of observations required to split a node. Instead of assigning fixed values, we set these parameters to tune, indicating that we will optimize them later during model training. We then set the model engine to Ranger, a fast and efficient implementation of random forest in R. We also enable permutation-based variable importance, which allows us to assess how much each predictor contributes to the model's performance by measuring the impact of randomly shuffling its values. Next, we define the modeling workflow by combining the pre-processing recipe with the random forest model. This ensures that all data transformations and model fitting steps are applied consistently within a single pipeline. Finally, we create a regular tuning grid that systematically explores combinations of hyperparameter values. We vary the number of trees between 300 and 800, mtry between 2 and 10, and mn_n between 2 and 10, each at 3 evenly spaced levels. This grid allows us to efficiently search for an optimal model configuration that balances accuracy and generalization. For efficiency's sake, we set up parallel processing to speed up model training and hyperparameter tuning. We first detect the number of available CPU cores on the machine and subtract 1, leaving a core free to keep the system responsive during computation. We then create a PSOCK cluster using the remaining cores. This cluster allows multiple worker processes to run simultaneously, distributing computational tasks across different cores instead of running everything sequentially. Finally, we register this parallel backend using register do parallel, which enables the modeling framework to automatically use parallel processing during operations such as cross-validation and grid search. This step is particularly important for computationally intensive models like random forests with hyperparameter tuning, as it significantly reduces training time and improves overall efficiency without changing the underlying model results. Now we perform hyperparameter tuning for the random forest model to identify the best performing configuration. We first set a random seed of 123 to ensure that the results are reproducible. We then run tune_grid, which systematically evaluates the random forest workflow across all combinations of hyperparameters defined in the tuning grid. For each combination, the model is trained and validated using the previously defined 5-fold cross-validation folds. To evaluate performance, we compute multiple metrics: ROCAUC to assess overall classification quality, accuracy to measure correct predictions, sensitivity to capture how well the model identifies positive cases, and specificity to evaluate how well it identifies negative cases. After all models are evaluated, we select the best performing configuration based on ROCAUC, which prioritizes the model's ability to distinguish between patients with and without heart disease across all classification thresholds. This step ensures that the final model is not chosen arbitrarily, but is instead optimized based on robust cross-validated performance across multiple evaluation criteria. We then finalize the random forest model using the best performing hyperparameter combination identified during tuning. We take the original modeling workflow and update it with the optimal values stored in best_RF, ensuring that the final model uses the configuration that achieved the highest cross-validated performance. Then we fit this finalized workflow to the full training dataset. At this stage, the model learns patterns from all available training data using the optimized settings for number of trees, number of predictors per split, and minimum node size. This step marks the transition from model selection to model training. Instead of evaluating multiple candidate models, we now commit to a single best model configuration and train it fully on the training data so it is ready for evaluation on the unseen test set. The result is a fully trained random forest model that is both optimized through cross-validation and ready for final performance assessment. Next, we build and tune an XGBoost model as an alternative to random forest, aiming to improve predictive performance through gradient boosting. We define a boosted tree model and specify several hyperparameters to be tuned, including the number of trees, tree depth, learning rate, and minimum number of observations per node. Each of these parameters controls the complexity and learning behavior of the model. We then set the engine to XGBoost, a highly efficient and widely used implementation of gradient boosting for classification problems. As before, we integrate the model into a workflow that combines the pre-processing recipe with the modeling specification, ensuring a consistent pipeline from raw data to predictions. Next, we create a tuning grid using a space-filling design. Instead of exhaustively testing every combination, we sample 15 diverse hyperparameter combinations across the defined ranges. This approach allows us to explore a broad search space efficiently while reducing computational cost. We then run cross-validated tuning using the same resampling strategy as before. The model is evaluated across multiple folds using ROCAUC, accuracy, sensitivity, and specificity, to capture different aspects of performance. Finally, we select the best performing XGBoost configuration based on ROCAUC, prioritizing its ability to distinguish between patients with and without heart disease across all classification thresholds. This step provides a strong alternative model to Random Forest and allows for performance comparison between two powerful ensemble learning methods. We finalize the XGBoost model by applying the best hyperparameter combination identified during cross-validation tuning. We take the original XGBoost workflow and update it with the optimal values stored in best_XGB, ensuring that the final model reflects the configuration that achieved the highest ROCAUC during evaluation. We then fit this finalized workflow to the full training dataset. At this stage, the model learns from all available training data using the tune settings for tree complexity, learning rate, number of trees, and minimum node size. This step marks the transition from model selection to final model training. Rather than comparing multiple candidates, we now commit to a single optimized XGBoost model that has already been validated through cross-validation. The resulting model is fully trained and ready for final evaluation on the unseen test set, where its generalization performance can be assessed and compared against the Random Forest model. Now, we generate predictions from both the Random Forest and XGBoost models using the unseen test dataset. This allows us to evaluate how well each model generalizes to new data that was not used during training or cross-validation. For each model, we first produce predicted probabilities using type equals prob, which gives the estimated likelihood of each patient belonging to the disease or no disease class. These probabilities are important because they allow for threshold-based decision-making and performance evaluation using metrics such as ROCAUC. We then generate class predictions, which assign each observation to a specific category based on the model's learned decision boundary. Finally, we combine these predictions with the original test dataset using bind_cols. This creates a single structured dataset that includes the true outcomes, predicted classes, and predicted probabilities side by side. This step is essential because it brings together ground truth and model outputs, enabling direct comparison and allowing us to evaluate performance using multiple metrics in the next stage. We now evaluate the final performance of both models using the ROCAUC metric on the unseen test dataset. ROCAUC measures how well each model can distinguish between patients with and without heart disease across all possible classification thresholds. We compute ROCAUC by comparing the true outcomes in the test set with the predicted probabilities for the disease class, explicitly setting event_level equals second, so that disease is treated as the positive outcome. The results show a very strong performance for both models. The Random Forest model achieves an ROCAUC of 0.997, indicating near perfect separation between the two classes. The XGBoost model also performs strongly with an ROCAUC of 0.965, slightly lower than Random Forest, but still reflecting excellent discriminative ability. This comparison suggests that both models are highly effective at distinguishing between patients with and without heart disease. although Random Forest performs marginally better on this dataset. At this stage, the difference in ROCAUC provides a clear quantitative basis for model comparison and selection. Now we move from overall model performance to interpretability by examining feature importance in the final random forest model. To do this, we first extract the underlying fitted model from the tidy model's workflow, which gives us direct access to the trained Ranger engine. We then use a variable importance plot to identify the top predictors that contributed most to the model's decision-making process. This importance is calculated using a permutation-based approach, which measures how much model performance decreases when each feature is randomly shuffled. By focusing on the top 10 most important features, we gain insight into which clinical and demographic variables are most influential in predicting heart disease. This step is essential because it shifts the analysis from pure prediction to explanation, helping us understand the drivers behind the model's decisions. Looking at the plot, we see that the two most important predictors are thal_x2 and thal_x3, which are categories of the thalassemia test variable. Their high importance scores suggest that abnormalities detected during cardiac stress testing are among the strongest indicators of heart disease in this dataset. The next most influential variable is old peak, which measures ST segment depression during exercise relative to rest. Clinically, higher old peak values are associated with reduced blood flow to the heart and are often considered markers of ischemic heart disease. The model appears to rely heavily on this variable when making predictions. Maximum heart rate achieved during exercise, represented by thalach, is also highly important. This suggests that a patient's cardiovascular response during physical exertion provides valuable information about underlying heart health. Age ranks among the top predictors as well, reinforcing the well-established public health finding that cardiovascular risk generally increases with age. Several other clinically meaningful variables appear lower in the ranking, including slope, which describes the slope of the exercise ST segment, resting blood pressure, TRES BPS, and cholesterol levels, THOL. While these variables contribute to prediction, they appear to provide less information than the cardiac stress test variables. In the next step, we interpret how a key feature, old peak, affects the model's predictions using partial dependence analysis. To do this, we first prepare the training data by applying the same pre-processing steps defined in the recipe, ensuring that the data is in the correct format used by the random forest model. We then generate a partial dependence plot for the variable old peak. This method shows the average effect of old peak on the predicted probability of heart disease, while holding all other variables constant at their observed values. This step is important because it moves beyond feature importance, which only tells us which variables matter, and instead shows how a specific variable influences the model's predictions across its range of values. It provides a more detailed and interpretable view of the model's behavior, particularly for clinical variables that have a clear real-world interpretation. This partial dependence plot illustrates how the variable old peak influences the random forest model's predicted probability of heart disease, while holding all other predictors constant. The x-axis represents old peak, which measures ST segment depression induced by exercise relative to rest. Clinically, higher values indicate greater abnormalities in the heart's electrical activity during exercise and are often associated with myocardial ischemia. The y-axis shows the model's average predicted probability of heart disease. At very low old peak values, the predicted probability of heart disease is relatively low, at around 41 to 44%. As old peak increases, the predicted probability steadily rises, indicating that patients with greater ST segment depression are more likely to be classified as having heart disease. The increase is particularly noticeable between approximately 1.5 and 3.5, where the model's predicted probability rises from about 48% to nearly 58%. Beyond an old peak value of around 4, the curve begins to plateau, suggesting that additional increases provide little extra predictive information because the model has already identified these patients as being at high risk. From a public health perspective, this pattern aligns well with established clinical evidence. Exercise-induced ST segment depression is a recognized marker of coronary artery disease, and the model has learned this relationship directly from the data. Next, we use SHAP values to interpret the predictions made by our final XGBoost model. While performance metrics tell us how well the model performs, SHAP helps us understand why the model makes its predictions by quantifying the contribution of each feature. We begin by extracting the trained XGBoost engine from the final fitted workflow using extract_fit_parsnip. This gives us direct access to the underlying XGBoost model, which is required for SHAP analysis. Next, we prepare the training dataset by applying the same pre-processing recipe used during model training. Using Bake, we transform the training data into the format expected by the model and then remove the target variable so that only the predictor variables remain. We then compute the SHAP values using the SHAPViz function. This calculates the contribution of every feature to each individual prediction, allowing us to see both the magnitude and direction of each feature's influence on the model's output. Finally, we visualize the results in two ways. The first SV_importance plot ranks features according to their overall importance based on their average SHAP values, providing a global view of which variables have the greatest impact on predictions. The second plot uses the beesworm option, which shows the distribution of SHAP values for every feature across all observations. This visualization not only highlights feature importance, but also reveals whether higher or lower feature values increase or decrease the model's predicted risk. Looking at the first plot, we see that the most influential predictor is CP_X3, which represents one category of chest pain type. This finding is clinically meaningful because chest pain characteristics are one of the strongest indicators used in the diagnosis of coronary artery disease. The second most important predictor is Thale_X3, a category of the thalassemia test variable. This agrees with the Random Forest analysis, suggesting that abnormalities detected during cardiac stress testing are consistently among the strongest predictors of heart disease. The variable old peak also ranks highly, indicating that exercise-induced ST segment depression has a substantial impact on the model's predictions. This aligns with established clinical evidence that greater ST segment depression is associated with myocardial ischemia and cardiovascular disease. Other influential variables include REST ECG_X1 CP_X2 and slope_X1, all of which are derived from electrocardiographic findings or exercise stress testing. This suggests that measures reflecting cardiac function contribute more to prediction than many traditional cardiovascular risk factors. Variables such as age, cholesterol, maximum heart rate achieved, and resting blood pressure also contribute to the model, although their average influence is smaller. While these factors remain clinically important, the XGBoost model relied more heavily on exercise and electrocardiographic variables when distinguishing between patients with and without heart disease. The SHAP beesworm plot provides a more detailed explanation of how individual variables influence the XGBoost model's predictions for heart disease. Each point represents a single patient in the dataset. The position along the x-axis indicates the SHAP value, or how much that variable increases or decreases the predicted probability of heart disease for that patient. Points to the right increase the likelihood of heart disease, while points to the left decrease it. The color of each point represents the value of the predictor. Purple indicates relatively low values, while yellow represents relatively high values. At the top of the plot, CP_X3 has the greatest overall impact on the model. Most observations are associated with negative SHAP values, indicating that this chest pain category generally decreases the predicted probability of heart disease. In contrast, thal_X3 shows predominantly positive SHAP values, suggesting that patients belonging to this thalassemia category are much more likely to be classified as having heart disease. The variable old peak displays a clear trend. Higher values shown in lighter colors are concentrated on the positive side of the plot, indicating that increasing ST segment depression raises the predicted probability of heart disease. Lower values tend to appear on the negative side, reducing predicted risk. This pattern is consistent with established clinical evidence. For age, higher values are also generally associated with more positive SHAP values, indicating that older patients contribute more strongly towards a prediction of heart disease, although the effect is less pronounced than for old peak or the stress test variables. Variables such as cholesterol, maximum heart rate achieved, and resting blood pressure show more dispersed SHAP values. This suggests that their influence depends on the combination of other patient characteristics rather than having a simple linear effect. Before concluding the analysis, we perform a cleanup step by stopping the parallel processing cluster that was created earlier in the workflow. Throughout model training and hyperparameter tuning, parallel computing was used to speed up computation by distributing tasks across multiple CPU cores. Using stop clusters CL, we properly terminate the cluster and release the computing resources that were allocated during the analysis. This prevents unnecessary background processes from continuing to run and ensures that system memory and processor resources are freed. This final step is considered good programming practice as it leaves the R session in a clean state, avoids resource leaks, and marks the successful completion of the machine learning pipeline. And that brings us to the end of this machine learning analysis comparing Random Forest and XGBoost for heart disease prediction. In this workflow, we prepared and explored the data, trained and tuned both models using cross-validation, and evaluated their performance on unseen test data. The Random Forest model achieved the strongest predictive performance for this dataset. Beyond prediction, we used feature importance, partial dependence plots, and SHAP values to explain how the models arrived at their predictions. These techniques highlighted cardiac stress test results, chest pain type, and electrocardiographic findings as the most influential predictors, while age, cholesterol, and blood pressure also played important roles. Overall, this analysis demonstrates that machine learning can provide both accurate predictions and valuable clinical insights, supporting earlier risk assessment and more informed healthcare decision-making. In the next video, we'll shift our focus from supervised machine learning to unsupervised machine learning by exploring clustering techniques. Specifically, we'll learn how k-means clustering groups individuals into similar clusters based on shared characteristics, and how hierarchical clustering builds a tree-like structure to reveal natural relationships within the data. I'll see you in the next video.